Welcome to AI for Good, the leading action-oriented, global and inclusive United Nations platform on AI. Organized by ITU, in partnership with 40 UN sister organizations, and co-convened with Switzerland. The goal of AI for Good is to identify practical applications of AI to advance the United Nations Sustainable Development Goals and scale those solutions for global impact. In today's session, we're counting on you to use the live video wall feature to ask questions and post comments to help create an engaging discussion. We encourage you to stay until the end to chat, connect, ask questions, and network with our distinguished panelists and world-class AI experts in the neural network. It is now time to kick off the session and welcome our first speaker. The floor is yours.
Thank you, Anna. Hello, everyone. Good morning, good afternoon, good evening from me as well. I'm Guilherme Martinez Roura from the International Telecommunication Union, and I would like to welcome you all for joining today's AI for Good webinar on intelligent robots for space science and planetary exploration, organized by the ITU together with UNOOSA, the United Nations Office for Outer Space Affairs. This session is part of the AI for Good robotics programming track, exploring how AI-powered robots are helping to unlock our human potential and advance the United Nations Sustainable Development Goals. We have a distinguished set of panelists today, but as always, we are counting on you, the participants, to help create a very interactive session. Without further ado, I would like to introduce our moderator today, Dr. Marco Pavone. He is Associate Professor of Aeronautics and Astronautics at Stanford University. Marco, welcome, and the floor is yours.
Thank you very much. It is a pleasure to be here, and I look forward to discuss with all of you the topic of AI and space robotics. But before starting, I would like to give the stage to Jorge for a very quick introduction.
Thank you very much, Marco. Thank you, Guillem. Let me share my screen. I hope you can see it. Maybe not yet. So good afternoon, all. Thank you very much again. As I said, I'm working for the United Nations Office for Outer Space Affairs, and it's really my pleasure to be here today. And it's a pleasure to partner with ITU for this session and to share the stage with my fellow panelists here. Thank you all for attending. There are probably some of you in the audience that didn't know about UNOOSA, the United Nations Office for Outer Space Affairs, so I'm going to make a very quick introduction to the office. The United Nations Office for Outer Space Affairs is basically fulfilling three roles in the United Nations system. We are a convener. We facilitate international cooperation among UN member states to basically develop new space policies, space treaties, and guidelines. We are also a gateway in the United Nations system. We are the only UN agency that is devoted to space-related affairs. And we are also a capacity builder. So basically, we provide to member states, we provide capacity building so they actually can get up to speed and to learn new technologies and apply new technologies for sustainable development. We are based in Vienna, as I said. One of the functions of the office is to be the secretariat of the Committee on the Peaceful Uses of Outer Space, which is called COPUOS. There in the screen you can see COPUOS has a membership now today of 100 member states. UNOOSA is the secretariat of COPUOS, which is the UN Committee for the Peaceful Uses of Outer Space, and today it has 100 member states. You can see the list of the member states down in the screen, and you can see there that it's not only about established space countries, but it's also about emerging space countries, and it's about countries that don't have, in some cases, even a space agency established. That's why it's very important, the role of UNOOSA as capacity builder, and also to bring together and put together this discussion forum that is COPUOS. With that broad membership that I was mentioning before, we have seen that there is a problem that exists, which is called the space divide, which is basically the gap that exists between countries that have capabilities, space capabilities, and well-established capabilities, and those that don't have those capabilities. Of course, this is a spectrum. It's not from black to white suddenly, but there are a lot of grays in the middle. And in the office, we are supporting member states in acquiring those capabilities to basically to reduce the space divide. There are a number of projects in the office, and you can see a glimpse of those there in the screen. I'm not going to go into the detail, but you see the wide range of activities that are related to space that can be actually applied to support sustainable development here on Earth. The one which I'm going to speak a little bit more is about Access to Space for All, which is an initiative that is basically providing opportunities, access to facilities, access to research facilities and infrastructure, information and education to bridge that space divide. And you can see some of the facilities that we have access to in the under that initiative. We have access to the International Space Station, we have access to the Chinese Space Station, we have access to ground-based infrastructure, we have access to rockets, to satellites and hosted payloads. So it's a wide range of facilities that we offer and put together for member states and institutional member states to actually get up to speed into developing technological capabilities. We have arranged those opportunities under 3 tracks: hypergravity and microgravity, satellite development, and space exploration, which is very much of concern here today. And those 3 tracks are arranged in that way to develop a capability in the member states: the capability of developing experiments on orbit, the capability of developing satellites, and the capability of engaging more in space exploration. We cannot do that without the partners that we have, and we are partnering with the space agencies, research institutions, and universities and the private sector to do that. And I mean, some of the speakers here are from some of the organizations we are partnering with, so I'm very happy to see that. In one of the experiments, in one of the opportunities that we offer, we basically it's a technological development and technological demonstration opportunities that can be used by member states. Unfortunately, the video cannot be played. I don't know why, but there was a team in Costa Rica that was testing robotics in microgravity. How robotic arms would behave and what would be the different behavior from ground, 1G, to microgravity environment. And that was thanks to the opportunities that are offered by the office. So they were able to access the infrastructure and to start gathering and acquiring data and know-how on how to develop technology that can later on fly to space. And basically, I would like to start with more questions than answers, because we are going to be discussing about AI and robotics and planetary exploration. But I pose the question to my fellow panelists: can the combination of AI and robotics reduce the space divide, or do you think it will widen it? Which are the opportunities that exist for developing countries in this context, in the context of planetary exploration, robotics, and artificial intelligence? And how can we make space exploration more inclusive? And I have one example that I was testing a couple of days ago, which is, the space agencies, well-established space agencies, already have a corpus of data, not only data that is coming from the planetary exploration missions, but also from the engineering process that have led to that. As we all know, artificial intelligence, machine learning algorithms are powered by data. So if you have strong corpus of data, you have advantage in terms of putting an algorithm that is able to provide you better results than if you don't have enough data. And I was doing a test with an open artificial intelligence, OpenAI platform that is available for anyone. And I was actually testing the platform to write for me documentation on space exploration and robotics. And I asked, the questions that I asked to the artificial intelligence was, write are in bold, write a requirement for a robot for space exploration, write a requirement from a spacecraft for the exploration of Jupiter, write a requirement for a probe orbiting Mars to indirectly study the core of Mars, name commercial brands of high-power transmitters in case we want to set up communication with a probe, and write a test case for communication, for a communication system able to handle multiple messages being sent at the same time. And you can see that the answers there are not perfect, but are not that far from the initial stage that an engineer will take to actually be writing those requirements, those test cases, and be surveying the market for actually putting the systems into reality. So again, my question, how this technology can help developing countries to actually embark and be better in space exploration, while all this data, including the data of the engineering processes, is held by established space agencies. And with that, I would like to thank you very much, Marco, for giving the floor for the introduction.
Thank you very much, Jorge, for a nice overview of the UN Office for Outer Space Affairs. Now, as most of you know, in the past few decades, robotic systems have allowed us to explore the solar system, allowing us to better understand its origin, its evolution, and its potential habitability. AI technologies have certainly played a major role in designing such space robots, and will arguably play an even bigger role in the future. So the goal of this webinar is to understand in more detail how AI is shaping space robotics. Specifically, the goal of this webinar is to overview and discuss what are the key capabilities that the AI has enabled for space robotics, what are the key open problems related to AI in the space robotics field, and what are the most exciting opportunities for future research and development. We are fortunate to have an amazing panel to discuss this theme. The webinar will comprise 4 10-minute talks. The first one will be given by Dr. Gianfranco Visentin. He will start with a broad overview of applications of AI in space science and planetary exploration. And then we're going to have 3 deep dives. So specifically, Dr. Vandi Varma is going to provide a deep dive on AI applications in the context of Mars operations, Mars rovers, Mars helicopters, super exciting. Dr. Yang Gao is going to give a deep dive on AI applications in the context of orbital missions, along with the discussion about sustainability of space robotics. And then Dr. Aline Abu Shaffer is going to provide a deep dive on AI for intelligent robots interacting with astronauts. And finally, we're going to have a Q&A where I invite you to ask your questions. We will be down selecting some of the questions, and we will then ask those to the panelists. With that, we're going to start with our first talk from Dr. Gianfranco Visentin. Dr. Gianfranco Visentin is currently the Automation and Robotics Section Lead at the European Space Agency. And in this capacity, he's responsible for the technology development in the field of space robotics at the European Space Agency. With that, Gianfranco, the stage is yours, and I look forward to your talk.
Hello, everybody. I'll start my presentation. So I'm going to very quickly talk about what we do in AI at the European Space Agency, but also how we promote the role of AI within the European Commission and European Union activities. So first of all, it's important to see what is the perspective of this talk. And the perspective is essentially, do we have a discussion in which robotics is the main actor and AI is, let's say, a tool used by robots, or the other way around? Well, I am a roboticist, so for us, we have AI as a tool. And I would like you to essentially show to you that we have already used AI for very many uses. And this hopefully introduces also the aspects of the other speakers in this webinar, where they will show how AI is applied to the different uses. AI is a big thing. So there are many, many different technologies. In fact, the classification of AI as is a bit difficult. There are very many ways of classifying. I'm showing one. Essentially, AI is a set of disciplines, of tools that allow to solve different problem domains using different paradigms. What are the problems we typically have in space exploration? Essentially, we have different problems depending how far we're looking in the future. We like to see the future split into 3 different horizons: a short term, mid term, and long term. At the moment, we have rovers in planets, and they are working with increasing autonomy. And hopefully in the midterm, this will continue to grow, in which way we can work for entire days, if not weeks, of robotics being completely independent and communicating results of their activities back to Earth. In the future, AI, and from midterm to long term, we see it will be instrumental to allow access to very difficult sites. We're talking about the caves, the cliffs, the places which do not guarantee continuous communication. So once a robot system enters there, it's completely alone. It has to mind for himself. Finally, for an established permanence of humans in space, we see that in situ resource utilization done by means of robots and construction of infrastructure is essential to enable humans to go back to space. At the moment, of course, the main use is autonomy. And the typical problem of a rover going around is essentially being in a place and go in a given time somewhere else. And this is something that requires a lot of ability, of physical ability. So robots that can cope with this terrains, which have a very different types of obstacles, but also a good navigation, because essentially the problem is that you have to go from here to there, and there are obstacles, and you can do 2 things with obstacles: either go over them or go around them. So the logical autonomy, what AI can do in this, is extremely important. So how do we use in moving robots, in mobile robots, and in general robots, autonomy? We have very many different technologies. Well, so we like to use this 3 layers architectures, and I have tried to put together all the different technologies of AI that we are using. So for example, we have for what regards the mission layer, which is where you tell the robots what to do, we have tools coming from the temporal planning and scheduling. For what regards the navigation layers, which enables the system to essentially go around with obstacles, we have computer vision, which is considered also a branch of AI. And again, we need to do path planning in order to determine what is the right path to follow, having perceived the environment. And finally, we are working in a style environment. So things need to work in a given time. So you need also temporal planning, not only spatial planning. And this goes on also for lower layers, whereby, for example, if you are implementing the navigation requires a lot of detecting technology, and this can be implemented with computer visions or computational neural networks, or artificial or simple artificial layers, in order to ascertain and derive from the information that is coming from all the sensor, the evolved information that allows the system to take decision and affect the planning and scheduling. Planning and scheduling is an important part. I've been mentioning a lot, and I guess you will hear a lot more in the following talk. So what is planning? Is devising a plan of action to achieve one goal. So what to do and in which order. Scheduling, conversely, in our world, is when and for how long, how much you will do those actions. This is a typical problem of AI. And for example, in the cold Martian environment, you have to do these things respecting constraints, like having enough energy for the battery, and at the same time having enough time to warm up to operational temperature of the subsystems, so that you can do what you're expected to do, but automatically switching on the things that will enable your operations. We have been working, for example, on the planning and scheduling on the possibility that things go wrong. In fact, we plan activities here on Earth, but then they have to be executed on Mars. And things can go wrong because actually we don't know what is going to happen there. So the systems have to have enough ability to essentially change the plans. And we see that there are two capabilities. One is a simpler plan repair. So essentially the planner system on board of the rover can replace things which cannot be executed because the conditions are not appropriate. And then there is a further development which is needed for the longer term autonomy, which is complete replanning. So as the robot cannot execute due to the contingency what is expected to do, it can invent on itself something that will still be good for the execution. This is really showing the two differences. So if you have an original plan when you have activities that cannot take place and the plan is broken, you see this blue part which is making the broken sign, you can replace with the replanning activity and having something that is still worth doing in the time that the system has. And maybe do something else just fitting the time. Instead, replanning, when you break the plan, you essentially do a completely different thing, which was not part of the options before, but the system may decide that, you cannot go forward, we can maybe backtrack and do for other routes. So these are the fundamental differences we see. Other opportunities that are given by AI is, of course, on the decision of where you are going. You see, in the replanning work, you have to have some sort of an idea of what is an alternative goal. And so AI, for example, allows you to make a classification of the terrain where you are, and it allows to detect things that are worth investigating, or in some other cases, discover autonomy, things that are not matching anything of your previous knowledge, and it's maybe worth having a look at. We're doing all these things with ESA, but also with the European Union. This is a roadmap we put together, building up specifically a number of building blocks in which AI was very important. And I am just showing you some of the examples of the things we have done. We put together an entire European robotic goal-oriented autonomous controller, which is essentially allowing doing this planning, rescheduling, scheduling of essentially time and spatial activities. So mixing together where to go and when to do it. We have been working on advanced autonomy, also looking at these aspects I was mentioning, like the ability to replan completely something if you have the time. So doing what we call opportunistic science. So if the rover can see something that is really worth looking at it because it doesn't fall in anything that it has seen before, then the planner can consider exploring, at least visually, those elements. And we've been building on top of it for more applications, like in the preparation of infrastructure. The project was essentially putting together various differently able robots in order to build the infrastructure. This was particularly a 3D printed wall in order to create enclosures for human bases. And the last activity, we had just a preview today in the conference I am right at the moment, is where we essentially have different robots which are enabled with different capabilities, and they can allow the exploration of a skylight in a lunar cave. So lots of recipes, elements, we do the ingredients, but we also try to put together the applications. And hopefully, if the international context allows us, we'll also be able to deliver rovers to the planets. And that's what I wanted to say.
All right, thank you very much, Gianfranco, for the very nice overview. So our next talk is going to be given by Dr. Vandi Verma. Vandi is the Deputy Section Manager for Mobility and Robotic System at the NASA Jet Propulsion Lab. And she's also the Chief Engineer of Robotic Operations for the Mars 2020 Perseverance and Ingenuity rovers. More simply, Vandy is one of the drivers of the NASA rovers on Mars. With that, Vandy, the stage is yours.
Thanks, Marco, for that introduction. So, it was really interesting to hear Gianfranco talk about the broader picture. And what I'm going to go into a little bit is talking more about how in the recent past, the robots we've had on Mars, they're just getting increasingly autonomous. And this is because we actually have challenges and problems that we can only solve with AI and autonomous capabilities. I'm going to focus more on the most recent mission that I've been working on, which is the Mars 2020 mission. And it has the Perseverance rover, which is shown in the picture, and the Ingenuity helicopter. But actually, Perseverance is part of this much larger international mission, which is the Mars Sample Return mission. Perseverance is the first step where it's collecting from a very distributed region on Mars sample cores, so that for the first time we can bring back samples to Earth and study them in all of the laboratories on Earth. Even though we send instruments and can analyze things on Mars, what we can do in the labs on Earth is significantly greater. So Perseverance is going to collect these cores, and then it's going to bring them and drive over to a lander that's going to land on Mars, which is a joint European Space Agency, ESA, and NASA mission. And it's going to land a lander with a 7 degree of freedom robotic arm, which can collect the samples from Perseverance, put them in an orbiting sample canister, and then the Mars Ascent Vehicle, which is shown here, is going to launch them into orbit. There's an orbiter in Martian orbit that'll be an ESA orbiter, the Earth Return Orbiter, which is going to rendezvous with the Mars Ascent Vehicle, and then we're going to transfer the sample canister to it and get back to Earth. Because the helicopters have been so successful, we also have a backup plan where we have 2 sample retrieval helicopters. These are Ingenuity with wheels and an arm that are also capable of collecting the samples that are depoted and bringing them to the lander in order to make sure that we are able to bring the samples back. So when we were going to do this very large mission, which is a collaboration with lots of different countries, we want to make sure that the place we go and get the samples from was really interesting. And there's a huge set of scientists who got together.
Sorry,
and this is where
sharing the presentation in presenter mode.
Sorry, is it not in presenter mode? Are you seeing?
Yeah, basically
I think you might be seeing my different screen. So let me just switch screens. Sorry about that. Thanks. Let's see if this swap displays. Do you see it in presenter mode now?
Not.
Is it in presenter mode, Marco, or no?
No.
Interesting. Let me just stop sharing and try again. Give me 1 second. Just going to mirror my displays, and that might fix it.
Yeah, I think that's the simplest.
Yeah, I think I might just have.
Well, in the meantime, if you're not familiar with Ingenuity helicopter, I encourage all of you to get familiar with it.
Yes.
My 4-year-old daughter is particularly enthusiastic about it, and she keeps asking me if I can buy her one of the helicopters that fly on Mars. So I don't know about that, Mandy.
Are you seeing it now in presenter mode?
No, unfortunately, we don't see your screen yet.
I see. Let me just, I realized I actually stopped sharing. I'm going to share again and then try this. And this method. Okay, and I'm going to, okay. And let me just fix this.
Yeah, if you just swap display. Yeah, let's see. Great, thank you.
Okay, thanks for that. So yeah, just continuing in this. So one of the things we did with this mission was to say that instead of limiting yourself to where we could land because of the capabilities that existed, where do the scientists really wanted to land? And they wanted to land in this place which actually had a lot of hazards. There were crater walls that were really tens of meters tall. And we were able to do this because we decided to solve the problem of being able to land there by using autonomous capabilities. Whereas Perseverance was entering the atmosphere on a parachute, we're taking images and then using a pre-registered map to determine if it was actually going to end up landing in a hazardous location and had the ability to divert. So this really allowed us to be like, instead of limiting ourselves, let's actually think outside the box. What can we do if we were to deploy AI? And on landing day, this was really interesting. We were all in mission control waiting to see where in this blue circle, which was our landing ellipse, Perseverance was land. And it was actually headed for this crater, which would have been a hazard. And it did divert to the other safer side and was able to land in a safer location. But this also meant that we were now all the way across on the other side of the delta and had to plan a path to drive. And here I'm showing what we've actually driven. This is showing up to Sol 443. And most of this, so we did some opportunistic science because we were at the crater floor, why not do some science, but then started driving very fast using autonomous self-driving capability all the way to the delta. We were able to do this in the order of a month, which is kind of really a huge leap over prior missions, using mostly autonomous driving, so we didn't have to be limited by what we could see from the previous parking pose. And today, is much further along than this. The rover has driven over 13 kilometers and collected 14 cores, and Ingenuity at that point had flown 31 flights shown in the green, but since then we've actually flown 2 more flights, which is 33 flights now. And here I'm showing how we were able to improve the capabilities. So we actually have a second computer, which is dedicated to the self-driving and do the stereo processing needed in hardware in an FPGA. And these images you are seeing are taken by the cameras and done stereo processing and are the ones actually used for the driving. This is along South Seta, we were driving autonomously to enter into the region. And at the bottom right, you're seeing how those images are taken to convert into a terrain map to determine what the best path for the rover is to drive. And all of these images are publicly available on our sites as well. So autonomous navigation was possible because we made it faster. On the left, you're seeing the distance in each type of drive mode, and on the right is how long it takes. And the orange is autonomous driving, and the other colors are different modes of driving, whereas the blue at the bottom is actually driving where the drivers on Earth tell it to, and the others are gradation. So we've actually done 80% of the driving we've been able to do autonomously. Previously, we could do about 6%. So the advances that we've made in the area of autonomous navigation are really opening up the possibilities in space exploration to the point where we actually depend on it. It's not just an experiment, we're actually using it to drive most of the time. But it creates new challenges. So as we are driving, we would stop all the time and we would give scientists opportunities to get science observation. So on the left, I show a picture where we take, after we park, we take a image of the area around us, and that's in the tool we use where scientists are then able to pick, this is a really interesting feature, and I want to do a pinpoint targeted pointing, which you can do more accurately from a parking spot. And here you're seeing an example of, in the middle, the remote micro imager image, and on the right, where we shoot it with a laser in a drill hole and are able to study it. Now you start to lose this opportunity if you're just driving along and are not seeing things because Earth doesn't have time to intervene. So additional capability, this is like, why not solve this with AI? And we now have the ability on the rover, which we've had in previous missions as well, where we take a wide angle image shown here on the top left, and then on board with AI techniques and machine learning techniques, figure out what is the most interesting feature. What are scientists interested in? What would humans have picked? And then characterize it and automatically take these high resolution images without needing ground to figure out what's interesting. And here are some results where on Perseverance, this image that is the orange image is taken with our navigation camera. That's a navcam image. In it, running Aegis, we found the 2 of the more interesting rock features on Sol 442. and took a detailed image. Whereas if we had blindly targeted it, we would be targeting soil. Now we can actually find interesting science using AI techniques on board. And then other parts of this is, pushing the envelope of capabilities. In space exploration, we have to, trade off risk and benefit. We really wanted the ability to be able to know, flying allows us to access more different regions, allows us new capabilities. So we had a helicopter, Ingenuity, strapped under Perseverance, which was deployed to the surface. And we're able to demonstrate that in the 1% of Earth's atmosphere, which is what Mars' atmosphere is, and the really extreme conditions, which a 1.8 kilogram helicopter can survive, we were able to demonstrate, yes, that is possible. And so this is video taken by Perseverance's camera of Ingenuity's flight, showing that we now feel comfortable actually knowing we can reliably fly on Mars. This too requires a lot of AI capabilities, because as you're flying, you really can't intervene in that. So the helicopter takes images with its cameras, and it's using techniques in order to determine that navigate on the terrain. And it's flown, as of this slide, it's showing 31 flights, but we've done 2 more since then, and covered over 7,000 meters. The longest flight that has been demonstrated is 704 meters, lasting about 161 seconds. So there's a lot of new capability, and we feel so comfortable in that this has now been included as part of the baseline in the sample return mission. And just ending with, as we get ready, the most bright purple dot shows approximately the area in Jezero where we may deploy our first sample cache, and then we're going to climb onto the delta and explore beyond. And there are more autonomous capabilities that we're deploying that are going to allow some of this exploration to happen. As Gianfranco was mentioning, planning is one of them. So we have an onboard planner that we're getting ready to deploy. Its goal is going to be more of plan repair, but also the ability from a set of predetermined activities to add extra goals if we were able to, there were reason to alter the plan. And also autonomous manipulation and a lot of other new capabilities that we will need as we continue to explore beyond. So I'll just end with that. And there's a lot of information about these on the Mars site and the robotics website at NASA.
Thank you very much, Wendy, for a very fascinating talk. Next, we're going to hear from Dr. Yang Gao. Yang is a professor of space autonomous systems, and she's the head of the STAR Lab at the University of Surrey. She's been working on a number of different aspects related to space robotics, but today she's going to focus particularly on the AI applications in the context of orbital missions. So with that, the stage is yours, Yang.
Thank you, Marco. I'm just confirming colleagues can see my slides, okay?
Yeah, we can see your slides well.
Excellent. So hello again, everyone. Thanks for taking your time listening in. Today I just want to share some of our latest work and findings in AI-enabled robotics with a long-term vision to help achieve sustainable space exploration and exploitation. As Marco already mentioned, I would like to probably be a bit more complementary to the previous talk by my colleague. I'm more looking into the orbital mission scenarios where there is a recognition that AI is very much required to help advance robotic capabilities for future spacecraft, so that we can realistically achieve some of the next generation of orbital mission concepts, such as active debris removal, on-orbit assembly, manufacturing, servicing, constellation, formation flying of satellites, and more reconfiguration systems for better lifetime extension, mission adaptability, and even potential cost saving for missions. From a technical point of view, space robots has to really deal with different mission scenarios. For example, have to interact with cooperative or non-cooperative targets. They have to be deployed either from pseudo-fixed platform or free-flying platform. So this all imply, in fact, different difficulties and challenges that the robotic system has to deliver and cope with. And that's where artificial intelligence is recognized to be a very good solution for us to overcome those key issues. The first example I'm showing here on this slide is where we're developing autonomous visual-based relative navigation in orbit servicing assembly, where your servicing spacecraft is trying to approach and dock with a target object in space. In this case, you have some prior information about it and potentially even controllability over it. But I think the key, interest here is how we can minimize the computation, increase the speed of that process, so that we can potentially fly these techniques in a smaller vehicle. We can reduce the cost of the mission. So here the solution we are looking at is using convolutional neural network through deep learning, that we can build models of the target object. So you can see on the left-hand side of the film here, that is a data set coming from a real-world mission from NASA looking at Soyuz, and on the right-hand side is something coming out created by the photorealistic simulator we developed in-house that really can provide us a extension of that data set that would be required by the CNN to train and build realistic models so we can use in real time for post estimation. In this case, only a single lens camera is required. And to put that into a demo, so let's say this is a mission. We try to fly a service arm on the spacecraft that can go and dock with a space mirror segment for assembly tasks, so pick and place kind of task. So here, the servicing arm shown on the film on the left-hand side carry a single lens camera and the docking interface, which you can see the camera view on the top corner here in the film plate. And what is very interesting, at this very moment, you can see that the camera start to lose sight of the target, which is the mirror segment, but still because of the quite a reliability of the neural net solution or deep learning, that the docking is still quite successful. So despite of that loss of sight. Another kind of orbital applications looking at visual guided navigation from manipulation grasping. As you can imagine, when you have to deal with a non-cooperative target, such as a space debris, there are a lot of uncertainties, unknowns about debris. For instance, in this digital simulation, you can see this is of course post the rendezvous phase, where you can see the servicing arm on your service spacecraft carry a two-fingered gripper approaching example of a space debris in this case is the nozzle of a span motor. And you can appreciate the difficulty here because we're talking about a curved surface, it's metallic, reflective, and you just have two-fingered robotic manipulator to try to capture and also retrieve. So here again, we adopt a solution that is based on AI, and we just use a sparse point cloud as a sensing input, allow this whole process to be in real time. And what is, of course, this has to be validated using the test bed on ground, and you can see that how the solution is quite successful. I think it's particularly very interesting with the rigidization stage, which is the pulling stage, which you can see how the arm can very successfully pull the space debris model very well, and there's quite a robustness that has been demonstrated. I want to say a few words about looking into the future, because I think one of the key, beauty of introduction of AI into robotics is really about this potential of achieving a long-term goal that is really need to have a sustainable operation, we call long-lived operation, for the next generation of spacecraft, and which also involve more robust mobility and autonomy on board of those spacecraft. In the near or medium term, I just summarize a few bullet points here on this slide, which reflect my view on what I think are quite important to be addressed. Those sort of small steps we have to achieve for that long-term goal to be a reality. So here, obviously low computational, more high accuracy mapping perception, energy optimized locomotion mechanisms and control, and resource aware computation and parameter tuning. We need solutions that can reliably tune those parameters we know is quite intrinsic to artificial intelligence, a type of computing algorithms, and also the reconfigurability, the self-verification of both hardware and software in real time, that I think are very important, because we have to give the mission operators the confidence that AI is reliable, in all aspects of where we introduce them. So this is one example of our, relative low TRL research investigation into that long-term goal. So this really, I really think we need to move from weak AI to strong AI solution. What that means, in my opinion, is more about looking at generic or reusable software architectures from the beginning of space system development rather than an afterthought, so that at all the introduction of machine learning techniques, AI are quite reliable and can enable reconfigurability of a system. So here is just one example of our work that shows how in real time we can switch between different algorithms in the visual processing to facilitate these autonomous navigation or planetary rovers, where when you observe a decay in the performance in real time, you have that capability of switching between different vision processing technique. Another example of going, really toward that long-term goal is on the sort of AI embodiment aspect, because very often I find that we might underestimate how AI can really help support and enhance of our knowledge solution in terms of the locomotion design or mobility design. Very often I think we highlight too much on the computation side. So here we have this about inspired solution for surface mobility of future generation of small rovers, where you can see how we can introduce crawling behaviors that can get small rover vehicles out of the loose sand, which we know is quite a challenging situation for rovers if we want to cut down the mass of the vehicle. But at the same time, that bio-inspired solution can allow the small rover to negotiate with quite challenging obstacles, as showing that climbing behavior at the same time as a crawling. So as you can see on the film on the bottom right, where the small vehicle can climb this rock, which is over twice the height of the radius of the whale. So those are also very good examples of how AI embodiment, I call it, can really help enhance capabilities. And similarly, I have the next example is also to do with subsurface mobility. I think it's very important that looking in the future, a lot of these interplanetary missions look at the subsurface exploration, that meaning you have to have robotic means to access the subregulars, and very often you need to deal with granular particle material. And here again, we are inspired by the insects like the wasp and develop a drill penetrator that can work or penetrate quite energy efficiently in the microgravity environment. So here, as you can see from the DM digital modeling, that shows the principle of the drilling rely on the traction between the drill bit and the regulars rather than the rotary motion, which is rely on the overhead. So this has also been prototyped. So it's not just a concept, as you can see from the film played, and how this kind of wasp drill mechanism can actually work very effectively. So I think that's my last one. I try to keep my time within my budget, so that's hopefully that's a quick tour of some of the things we did, and hopefully that helps stimulate some of the discussions later on. Over to you, Marco.
Thank you very much, Yang, for this very nice overview of your work and more in general about the how AI capabilities are helping with the space robotics. So unfortunately, our last speaker, Alin, has had some issue with his computer, so I don't know if he will be able to join us. So as we wait, I would actually open the floor for questions. So please submit your questions, and we will be monitoring them in the chat, and I will ask them on your behalf. But in the meantime, to get us started, I have first a question for Mandy. As you know, in the field of self-driving cars, we talk about the disengagements and disengagement rates. That is when a safety driver has to take control of the vehicle because the vehicle is encountering some issues. So I was wondering if you have seen an analog of disengagements with the Mars rover. And if so, what was the rate, if you can disclose that, and what were the main causes?
Right. So I think in some ways, we can't have a safety driver take over because the lifetime delay between Earth and Mars is so great that by the time if a safety driver was to intervene, it would be too late. It can take 4 to 24 minutes. But we do have a similar equivalent where when we are sending our plan for an autonomous drive, so we know, and have some slides if we go into it more deeply that we could share. But the way we drive is on Earth, we plan a path and tell the rover this is the suggested path, and then it figures out if it needs to deviate from it. If it detects that it can find no path based on its algorithmic capabilities, that's when it will stop and call home. So one of the examples where we did have of that was it can detect geometric hazards, but it doesn't do as well with texture. So sand is still something that is harder for robots to detect, and it's prevalent everywhere on Mars. If you've seen The Martian, it's like a lot everywhere. And so we, from the ground, mark areas where they can't drive in areas that there's sand. But the uncertainty of the rover's pose grows, and we know that. So sometimes it can't navigate these narrow paths through these non-geometric hazards. And we had that encountered when we were going around South Seta, where there was a region almost 500 meters into the drive where it couldn't find a path through it. It was very little rest of the driving left. But those are some of the cases where then the humans come and we are able to negotiate much more finely through some of this hazardous terrain.
Okay, thank you very much. And as we wait for questions from the audience, I have a more general question to both you, Vandy, and Yang and Gianfranco. So if you were to choose, what is a key capability that you would like for AI to enable, but it hasn't been possible so far, either because the AI models or AI tools are not powerful enough, or because you don't trust yet the AI solution in a space robotic mission. There's a question for all of you, either Gianfranco, Yang, or Bandi, whoever wants to take the lead.
I'm happy
Bandi,
to
you can start, yes.
Okay, yeah, I just want to make sure if either of you want to jump in, just jump in. But I think in general, what's interesting is, as Yang was showing and as Gianfranco, there's a lot of work that is going on. So when we think of things where we think that AI can't solve this, somebody somewhere might be working on an aspect of it that they can. It might not be further along enough that we've proven it to be deployed. But one of the larger challenges just tends to be that when we're exploring new areas that we have very little data about. Now, as we go to the outer planets, we've been on Mars for a long time, but we're looking for deep space exploration. You might have a single image of another moon of Saturn or Jupiter, and now you're trying to deploy a mission which won't last very long. So it's about encountering situations where you don't have a lot of training data, and yet you need to be able to adapt to situations and anomalies that are beyond what you nominally expect and still accomplish the mission goals. That's something we have made a lot of strides on and can do, but in terms of being convinced that all the possibilities can be handled, I think that would be a really interesting area where AI can make a lot more strides.
Yang, do you
Sure. Yeah, I think it's a great question. I echo what Randy was saying, that as a community who work on AI robotics, I think at least I observe in the past 20 years, we as a community, it's never a problem of short of imagination, because I think as a community, very active, keep on pushing new ideas into the application domain of space. So it's another issue of short of imagination and that sort of encouragement to introduce new idea. But what I found in my experience is that one of the things is very challenging to do is look at the trustworthiness of introduction of AI into the real world application, because there are a lot of distrust and concerns about introducing artificial intelligence. In fact, to a lot of degree, it is a lack of actually true understanding of what AI offers and how it actually works, sort of very fundamentally. So I think I would like to see more effort, but it has to be a joint effort. It has to be a collective effort among academics, industrialists, end users, that need to collectively look at some development of AI, which we have to consider the trustworthiness, the design, the value, for example, verification, validation. Can we do it in real time? I think the answer is yes, but it's very difficult to do. There has to be a lot of effort that require knowledge, experience from all stakeholders in the space sector to really discuss it, understand. So I think that would be probably at least one of the high priority topic I would like to say being picked up by the community collectively.
Okay, thank you. Yeah, absolutely. I echo both your responses. So there is an interesting question from Jorge, which is about openness of research and openness of your work. And so the question is, particularly for you, Bandi, would the ML models, training data and input data be available openly for say, the Ingenuity mission and the Perseverance mission, so that other people can work on those and basically help collectively improve the capabilities for space robots? So basically, there is any plan to release some of the data set or some of the telemetry data, so that other people, for example, from the academic community, can also exercise their tools and benchmark their tools.
Yeah, so I think definitely, I think there's a lot of interest in people, there's multiple ways. So one is certainly through like the publications, which allows us to not share data, but as much talk about the concept. And then the Ingenuity F' software that it's based on, since you specifically were talking about Ingenuity, that is open source. So that is available to download and work with. That's, the code base and collaborate and extend on. And most of the processing that we do with the images is through the images, and the public site actually sees the images exactly the same time as we are doing in operation. So it actually comes straight through the channel and goes there to the images. In fact, as time has gone by, what was interesting, Ingenuity was new. So we had a pipeline for all the rover images. There wasn't initially one for Ingenuity, but now there is. And so you can get all of the images as well. And the corresponding data, there's a huge amount of data. So some of it is putting it in a way that is useful. And NASA's very interested in that. And there's a lot of work going on to figure out how to make this so it's actually usable, because there is so much data. The science data, which is a very international community, tends to be such that the scientists like to interpret it in some way and put it out. So the science data is also available. It's a very large group. There's hundreds of scientists from all over, and they work as a committee to determine how to responsibly release that data. So yeah, I think that's definitely happening, and hopefully there's more interest. And so there's AI for Mars, which has also taken data and images, which is more concerted for the case of learning that I think you were talking about from the rover's perspective, where the public can label images and work on them. So yeah, that's definitely a lot of interest in that.
So where all this information can be found in the links that you provided, or can you provide?
Right. So mars.nasa.gov, they go to raw images, has information of all the images. And then there's an AI for Mars, a site that has information on the AI access. And then in the Ingenuity page, there's information on F' and software available for that.
Perfect, great. So we do have a question from Germany. And this question is about basically verification and validation. So specifically, how much testing goes into preparing autonomous robots for space exploration? And in particular, how difficult it is to mimic some of the expected situations when testing on Earth, either with a ground-based analog or through simulation. So for example, for the Ingenuity helicopter, how much testing went into the mission, and there were any surprises during deployment?
I'll take a crack at that. So essentially, it's a great question, because there's you really need to do a lot. Testing is where we spend a lot of time, because once you've developed the algorithm, you need to know that it'll work in the environment it was designed for. So we start out very much like any development that you might do for other AI algorithms. You unit test the code at the algorithm level. Then you test it in the integrated software system, all in simulation. We have simulations in which we can run hundreds of simulations overnight through different terrains in order to test it. And then we actually have a Mars yard in which we create some specific scenarios and run an actual robot running those algorithms. We actually do it in two different ways. We have a robot called Scarecrow, which weighs on Earth the same as the full rover does on Mars. So it doesn't have the robotic arm, but it has the same ground pressure. And we run it with COTS, commercial motor controllers, so we can test it in a more rugged manner. And then the next step is we would run it on a full-scale Earth replica of the rover. So we have a whole slew of testing we do. We can almost never replicate exactly the situation on Mars, right? Because it's, so we try to do it in pieces. We might test the mobility system, we'll test the environment. And then when we are deploying it on Mars, if you saw my graph in the beginning, we were doing less autonomous driving, because we were driving in a careful manner, but mapping and saying, what would the autonomy algorithm have done? And then get on the ground the results to say, yes, it would have done the sensible thing. And then we go and actually execute it on Mars. So these are the steps. For Ingenuity, right, you can't test 1% Earth atmosphere as easily, but we had chambers where there were hundreds of fans to simulate the winds and then have the appropriate sort of gravity assist and other mechanisms. So you simulate as closely as possible the scenarios that you would have on Mars, and then do a lot of testing in simulation.
Great. And Yang, I think you also heavily rely on testing platforms, right, to test your algorithms prior to deployments.
Yes, I think in the sort of academia, if you like, typically work with a TRL level, maybe up to 5 before we hand over to industry for further development. I think that will go to the region that Wendy was mentioning. So prior to that, I think the typical approach is we quite rely on a lot of data sets that we call benchmark data sets. And this could be from pre-existing missions. It could be from, for example, photorealistic simulators. It could be from data set that from an analog side on Earth. And there could also be a solution that in some very intelligent way or a clever way, we achieve an augmented data set and build on everything that I just said. So it will be a combination of all those different source of data sets. And using that, you can try to validate the solution. Of course, any sort of involvement of machine learning, one of the kind of dependency in a way is that it needs to be trained using quite large volume of data sets. I think Wendy already mentioned the difficulty. Another thing I think we tend to do before we hand over to industry for something we think is, fairly confidently, useful, is that we will build, test bed, we call a ground test bed, which we try to artificially create or replicate or simulate what we think would be in the key challenges, either to the vision system or to the control system, those extreme conditions in space, and we try to simulate those, but physically simulate those in hardware system. So that's another typical sort of approach we use for validation.
Okay, great. So,
sorry, can I just quickly mention one more thing? I don't know if colleagues are familiar. There's something called in-orbit demonstrators, in-orbit demonstration missions. This particularly applies to orbital robotics. And there could be missions that I know a lot of commercial companies now support. I think NASA also made a lot of piggyback mission opportunity to people who work towards really novel ideas as in-orbit test bed. So actually there's this extra opportunity to validate something in space, but not in a sort of commercially viable setup yet. So though they are real world missions, but they are more like a test mission, a demo mission, before you can say, oh, I reached the confidence level that this can be commercially sustainable.
Cool. All right. So a question for Wendy. So you mentioned that compared to the previous rovers, the current rover can drive 80% autonomously as opposed to 6%. So I was wondering if you could quantify a little bit better how this performance metric translates into a benefit for the mission. So, okay, you drive autonomously 80%, and now what? Do you have a 10x increased return on the science of the mission? Can you give us a sense of how really that helps with the ultimate goal of the mission, that is clearly to gather science?
That's a great question, because I think one of the interesting things is like how we drive on Mars is part of the story of why this helps so much. So usually the way we drive is we get images from Mars, and they tell us where the rover is in its surrounding terrain. And the cameras are getting really amazing. So we can see a lot, but still we can't see over the hill or over the horizon because it's line of sight imaging is going to give. So if you were to just drive based on what we see and use things like visual odometry to get good state estimate, we might be able to drive, 70 meters or so. But beyond the horizon, we would then be driving into terrain. You can see it from orbit, but there's a lot of uncertainty in registration of the rover post to orbital data. And so that's tens of meters. And even though Perseverance is the size of a small car, still boulders, if it has, we don't design it to have bumpers all over it. It could bump into rocks. And so those would be hazards that from orbit we can't see, from orbital imagery resolution, that we need to avoid. So what it allows us to do is drive further. We can drive, like, for example, without ground coming in the loop for 700 meters. Now, why this becomes important is in a single day, actually, before I started working on Mars, I didn't appreciate as much. We drive very little part of the day. So even though there's daylight on Mars and we might be using cameras, you don't drive the whole day because the power on the rover is so limited. So we only get a few hours in a day to drive. So you're only driving for a few hours. Now you have to get the orbiter passes and information to Earth, which varies. So you don't get the data down every day for planning. So essentially, you could maybe drive for a few, if you had a week, you might have a total of few hours a day, have a total of 5 times that, and not be, if you don't want people working on the weekend, they wouldn't get data down. Now we can say on Friday, we send a plan over where the rover can drive back to back without humans having to come in and check over 3 days, over a holiday, over weekend. So that allows us to cover much larger distances with less Earth intervention. And so as an example, I was showing the rapid traverse where we just wanted to get to the next interesting site. We could do it on the order of weeks, which would have taken half a year maybe to drive if we needed to have data on the ground and humans intervene. So the way it's doing it is it's allowing us to get to different places on Mars very quickly.
Okay, great. So I have so many questions that I would like to ask, but unfortunately we are almost at time. I will end with a question from 2 students from Edinburgh in Scotland. So these are 2 mechanical engineering students that are trying to build a rover inspired by Perseverance. And so basically they're asking for some help. What would be some good resources? Is there any reference design or reference stack that is available that they could use to try to replicate to the best of their capabilities the rover?
Yeah, oh, that's so great. First of all, I'm so impressed. I'm so good they're trying to build a whole robot. But I think as we are starting to get robotics is coming into the mainstream, we have a lot more classes. You have parts available where there is a lot you can do with building in, hobbyists and students and others can build robots very capable. So in general, on the site, we have information. There's a whole education website wing of the NASA site, and they provide information resources for teachers trying to teach students and work with them, and also for students for how to do some of the work. I haven't specifically looked if we have like a design the rover, but I'd be very surprised if we didn't, but I could look into that. And the other part is once you start to get like cameras that can take images with similar constraints, right? We have hazard cameras low, navigation cameras high. You could even use some of the images that are available from Mars to say, if my robot got those images, what would it decide to do in it? So I think there's a long way they could go, and maybe we'll use the capabilities they come up with someday.
And with the very last question, of course, one of the main open source projects in the robotics community is represented by ROS, the Robot Operating System. Mm-hmm. So this is a question for Wandy, Yang, or Aline, whoever wants to take it. To what extent you use ROS or open source tools as part of your work?
I'm happy to answer. Oh, go ahead, Yang, and then.
Short answers extensively. Extensive. It created a very good generic platform. I think one of the beauty, as most colleagues know, is it's really easy, it's convenient to accommodate new developments, new pipeline and testing. Of course, it has some limitations in terms of how optimized the system is, but I think to us, from the kind of more low TRL development kind of group point of view, it's quite a convenient system. We also, I think there's also facilitation of openness. I think that's a point being repeatedly mentioned. That openness is something I think the ROS exchange in terms of development between different research groups is also made much more convenient if everybody use a common platform.
Vandi, Alin, any thoughts before we close about using ROS and other open source tools for space robotics?
I will add that we use ROS as well very extensively. So all technologies that we develop start at the lower TRL level. And even for the autonomous navigation algorithm that I showed, ROS was used extensively in the framework where we were doing a lot of simulated testing because it offers these tools that make it really easy to do. There's also an effort to do space ROS. And so I think there's it's great, and it allows for these collaboration with universities and students as well.
And where can people find more information about space ROS, if already available?
Yeah, so I think that effort is, I would have to look into it, but I think it should be available from the ROS. I could look into where we could find more information about it, but it's very much initial work on it to try and come up with it. So it isn't already available, but there's an effort to develop as ROS, space qualified ROS.
So I want to wrap it up, but keep receiving very good questions. So let me ask a new one, and this is from Manila. So there is a team in Manila that is trying to focus on the application of AI and space technologies in general to problems that have a direct societal impact. For example, in the field of agriculture, like in terms of orbital surveillance. So what can university researchers from a developing country do to address the so-called space divide? What opportunities are there to explore space tech with the potential limited resources? So I'm thinking about maybe CubeSat or open source projects, but I'm asking this question to everyone in the panel. What are your thoughts about enabling researchers in maybe developing countries to have a more active role in space exploration? But maybe we can try with, let's hear from both of you. So let's start with Yang, and then maybe Vandi, you can also share your thoughts.
Sure, I think this question is much appreciated because despite the fact there is this division in terms of capability, this is just a reality because it is true that space tech development takes years because it's has quite a high, if you like, entry criteria in a way, at least traditionally. But having said that, I think the things are really start to change and evolve into a new, we call new space era, is that we are seeing more and more commercial product has a way of go into space standard or because of the experience we are getting. And as some of you point out, the miniaturization of spacecraft, so that with CubeSat, and we see a lot of this development in developing countries, even at the school level. So this is not even lower than university level. So this is all very pleasing, very encouraging change of course and directions. So that means that the space application is going to be more and more open up in terms of who can engage and the capability building. So I don't think I can give much advice because being academic, the resources and influence we could have at academic sort of environment, it could be less useful and powerful. Nevertheless, I think it could be that in developing countries, we could be looking at using some of the bilateral research funding methods that to encourage collaborations, maybe at educational level, at the kind of early, so blue sky research level, that between countries, you can call it between developing and slightly more developed countries. I think those mechanisms are something I've seen, I personally have been involved So I think those are quite tangible mechanisms that can be used.
Great. And Vandi, do you have any additional thoughts?
Yeah, I think that, so there's multiple ways. We regularly work with students and professors at universities all over the world. I directly interact, especially when you're doing something new and different, the novel early TRL part. That's actually very reasonably easy to collaborate with someone anywhere in the world. And if you have an idea, we think it has potential, we can provide data as well. And I've done that with students in Europe and elsewhere as well. And some of them then go on to continue exploring it further, especially these ideas that we think are interesting. The other is, I think as Yang was mentioning too, like there are these opportunities. All of the instruments, when we do payloads on our space missions, they're competed. And there's a lot of, we have Meta, that's a Spanish instrument. And then we have a SuperCam, which is a collaboration with research in France. And so those are opportunities too, where if you have a specific payload that solves a particular problem, there are opportunities on mission, which is becoming the case for technology demonstrations. It themselves are sometimes treated as payloads, the robotics part. So there's that bigger picture of opportunities with grants there, but there's also much earlier work for researchers and students. And we work all the time. In fact, some of them come and do internships at NASA. The students will come and further work with us. So that's definitely a path, especially in robotics.
Great. And I would also be curious to hear the perspective of the United Nations on this topic. So maybe Jorge, why don't you share your thoughts?
Thank you, Marco. I'm going to share my screen briefly because actually, when we are talking about space, we are talking about space robotics and AI, it looks like so far reaching, right? And the question was particularly geared toward agriculture. So there in the screen, you can see some examples of seeds that are in the upper part of the slide and seeds that have been exposed to hypergravity and microgravity environments here on Earth. You can actually do that with very simple means. And actually in the Office for Outer Space Affairs, we offer the opportunity of utilizing the infrastructure that allows to do that. And the seeds that has been exposed.
Oh, I think we have lost Jorge. Well, too bad. I encourage you to check on the United Nations website, more information if available. With that, I think it's time to wrap up. Thank you very much, Yang, and thank you very much, Vandi, for sharing your thoughts and your knowledge. It has been really fascinating hour in the house, and I encourage all of the attendees to now join the neural network platform to network a little bit with one another and maybe some of the panelists. And with that, I'll give the stage back to Guilherme.
Thank you very much, Marco, for this great moderation, and a big thanks to our speakers, Vandi, Yang, Jorge, Gianfranco, as well as to all the participants for making it such an interesting discussion. We had lots of great questions and amazing insight into autonomous space robotics. And now we really encourage you to check out the AI for Good program online to see more robotic sessions that may be of interest to you. And our next robotics webinar will be in 2 weeks on Thursday, the 13th of October, on the topic autonomous drones for disaster risk reduction. We are very much looking forward to engaging with you in our upcoming event. And now is the end of this section and the start of the networking in the AI for Good neural network with the panelists and participants for the next 10 minutes. So see you all in a couple of minutes. And now I give the floor back to Anna for the closing informations. Thank you so much.
Thank you for participating in today's AI for Good session. We hope you've learned something new, innovative, and engaging in today's event. We now encourage you to continue the conversation on the live video wall in the neural network. Here you can ask questions, like and comment, share links, complete the poll, connect with interesting profiles, or speak one-on-one using the chat and video function. After the networking session, we invite you to explore the lobby, try the smart matching quiz, visit the virtual exhibits, poster boards, the eShop, and build your personalized AI for Good program. Let's shape the future of AI for Good.